In our last lecture, we have stopped here. The momentum distribution, we have written the expression as n of p dp equal to c p square q minus te the whole square by c square into dp. And this equation gives a spectrum shape and it vanishes at p is equal to 0 and also Te equal to Q. Here Te is the kinetic energy of electrons, Q is the total energy of the reaction, and P is the momentum of electrons. And using this, we have mentioned that we will get a spectrum like this. That is, when P is equal to 0, NP is equal to 0, and when P is equal to, that means that your value Te equal to Q, again you will be getting another 0 value. So between those two 0 values, you are getting a spectrum like this. And by writing the expression, you can write as n of p as c by c square, p square q minus te the whole square. And already we have an expression for te. Substituting that, this will be the expression. And now, keeping this in mind, our next aim is to have a distribution. That means this is the number with respect to momentum. But normally we are interested in the kinetic energy. That means it is easier to measure the kinetic energy rather than momentum. And also in the starting session, we have drawn a figure, that means the energy spectrum of beta decay. So this we have already mentioned. We have interested in energy spectrum for electrons with the kinetic energy between Te and Te plus dTe. For momentum, we have written it as P and P plus T. And we know that the total energy of beta particles can be written as its kinetic energy plus rest mass energy. T is the kinetic energy, and mec square is the rest mass energy, where me is the mass of electron and c is the velocity of light. So in that expression, Te plus mec square, the total energy, suppose you substitute the expression for Te, which we have already as p square c square plus me squared c raised to 4 minus mec square, and this is the rest mass energy, so plus mec square. So Te mec square will be getting as root of p square c square plus me square c raised to 4. And if you are squaring on both sides, on squaring this, it will be, that means Te mec square the whole square will be Te square 2Te mec square plus me square c raised to 4, and on squaring this side it will be p square c square plus me square c raised to 4. These two terms can be cancelled and you can get as Te square is 2Te mec square plus p squared c squared. So from that you can have an expression for p as Te square plus 2Te me square whole to the power of half, that means root divided by c. And already we have written the expression, that means we have this expression Te square plus 2Te mec square plus p square c square. You are differentiating that with differentiating that expression, so it is 2Te dt plus 2mec square dte equal to 2c square p dp. So on simplifying this, you can have an expression for p dp as Te plus MEC square by C square into dt. So we have the expression NPdP is equal to Cp square Q square dP. And here, suppose you substitute for this P, then P dP and Q. We have already written the expressions for P as Te square plus 2Te MEC square whole raised to half by C, P dP as Te plus MEC square by C square into dt, and Q as Q minus Te by C. That means you can write the values of P, dP and Q in terms of energy. So when you are substituting the quantities in the right hand side of this equation in terms of energy, this NPdP can be written as NTE dTE. So now you are substituting the corresponding values. So it is C into, this is the value for P and this is the value for Q square. Our equation is P square Q square dP. You are substituting it as P dP, then P alone as well as Q square. So this is P, this is Q square and this is for P dP. So you can get the expression for NTE as C by C raised to 5 Te square plus 2Te MEC square whole raised to half into Q minus Te the whole square into Te plus MEC square. And again, here also you can see that this equation vanishes at Te equal to 0. When Te is 0, this term will be 0. So on multiplication, you will get the value of NTE as 0. And also when Te is equal to Q, this term, the middle term is 0. So again NTE is 0. And this will be the figure you are getting. The expected energy distribution will be like this. So now we got the momentum distribution and energy distribution. And when you are observing, you can see that this is the one that we are getting using your Fermi theory. But we have already familiar with the energy distribution. It is like this. Here it has a maximum value and then decreasing. So that is the energy distribution for electrons. But for electrons, you are getting a curve like this. So there is some discrepancy between the theory and your experiment. But if you are taking the energy spectrum of beta plus, that means positrons, it will be almost like this. There, this graph almost fits. In the similar way, when we are observing or when we are considering the momentum distribution, for electrons, that curve is almost suitable, but it fails in the case of beta plus decay, that means positrons. So momentum is correct. Momentum distribution is correct for electrons and kinetic energy distribution is correct for positrons. So we are almost near. That means by making some corrections or there are some reasons for this deviation, and the main reason is due to the Coulomb correction, that you can just think as, suppose an electron is emitted. It is emitted with, it is a negative charge and your nucleus is having positive charge. So that positive charge is always trying to attract this, or it is not that electron cannot be easily liberated. In the similar way, if a positron is emitted, it has positive value, so it will be repelled. So if it is emitted with a small velocity, by repulsion it will get more velocity. So this type of a distribution due to Coulomb field can be easily understood. So in our next session, we will discuss the corrections we have to apply in this Fermi theorem.